Sawasdee krap. Hello everyone. My name is Kosuke Takano from Kanagawa Institute of Technology. How do you spend under quarantine for these 3 or 4 months? In Japan, the government lifted the state of emergency in the end of May. However, the number of the infected is increasing now, and I'm worrying about that. I hope the situation in Thailand is better now. On May 19, I presented on this title, Brief Survey of Challenging Information Technology for Coping with COVID-19. But at this time, I re-recorded this presentation again for Chula students. I will use the same slide as in May. Therefore, you might feel some data in the slide are a little old. But I think the essence of the story is not changed, and I appreciate your understanding to use the original data as on May. Okay, I'd like to start my presentation. COVID-19 has been spreading since the end of last year. As of May 5, the number of deaths due to COVID-19 has been about 250,000. And as of May 19, as of May 19, it was about 300,000, and until yesterday, July 14, the number of deaths is reaching almost 570,000, and the number of confirmed people, a very large number, about 30 million people. Thus, COVID-19 has damaged medical facilities, school facilities, economics, and many other important things over the world, so that it has caused us to change our lifestyle dramatically. In such situation, I get very frustrated. Therefore, I'd like to find something that I can contribute against COVID-19. At that time, some people were already contributing to craft technical tools to help combat the virus and save our lives. Therefore, I have been surveying such works of information technology and scientific analysis for COVID-19. In this presentation, I'd like to introduce such works for us to learn how information technology and scientific analysis can contribute against COVID-19. Through my survey, I found some useful articles. In particular, I thought these following articles are suggestive and reliable. First one is the website by Bill Gates. Gates Notes by Bill Gates. And the second one is a blog article by Professor Shinya Yamanaka, who won the Nobel Prize a few years ago. In Bill Gates' article, he claimed that developing a vaccine and treatment method is important and essential. However, it will take much time to develop. He wrote about this in April, and I still believe his opinion was all true, even now in July. That means quarantine life is a better way to avoid coronavirus. And if we have to go out, we need to very careful behavior not to be infected. Professor Yamanaka gives us many useful information in his article based on the perspective. In variety of information about COVID-19, his opinion was based on academic researches or actual data. Therefore, his opinion sounds very reasonable, and I can accept his opinions. In my study, I used the statistical data from this COVID-19 dashboard, which is produced by the Center for System Science and Engineering at Johns Hopkins University. This site still works and very useful. And the data provided by Johns Hopkins University are open to public. Therefore, Chura students and Kaito students can get it from this GitHub site. So wait a moment. This is a GitHub site of Johns Hopkins University. You can access this site and find time series data of COVID-19. And you can download the actual data of time series data of COVID-19. Okay, I want to change the presentation slide. So can we back to the presentation slide? Okay, let's start again. And this is a graph of time series number of confirmed people, which I made from actual data. From this graph, we can see that the situation in European country is bad as of April 30, May 1st. For example, Netherlands, Spain, Italy, the number of confirmed people is growing, so their situation looks very bad. Especially, the situation in the US is extremely bad. Meanwhile, the number of China looks converged from the middle of February. So this timeline is the middle of February, and the number of China is converging like this. So this means the situation of China is getting better. And this is a graph of number of deaths. We can see the similar tendency as the number of infected people. And this is a graph about the time series number of recovered people. This is a graph of recovered people. From these results, we can grasp trends, the number of infected people or dead people to some degree. However, in order to understand the growth of impact more quantitatively, we have to use another indicator that is used in medical research. The first indicator I'd like to introduce is doubling time. Doubling time can give a more intuitive sense of the long-term impact of growth than simply viewing the percentage growth rate. So here, X sorry. X is the time that has passed since you started measuring, and Y is the number of cases on day X, and Z is the number of cases on day 0. And this slide shows an example of how to calculate doubling time. So in this example, suppose that the number of cases went from 400 on day 0 and 800 on day 2. That means X is 2. And in this example, Y is 800 on day 2 and Z is 400 on day 0. So that we can calculate doubling times like this. Calculated result is 2 days. And this graph shows a time series doubling time that I calculated for 7 countries: Japan, Korea, Indonesia, US, Singapore, Thailand, and China. Please note when doubling time is longer, it means the situation in the country is better against COVID-19. In the graph, China is pretty good because the doubling time is very long. So this is the China data. And doubling time is very long. Therefore, the situation of China looks very good. The next, Korea. In Korea, doubling time is long, so that Korea, the situation of Korea is also good. So this is the data of Korea. And thirdly, Thailand is doing well against COVID-19. The data of Thailand is this. So the situation of Thailand is also good. However, the doubling time of Japan is not good. This is the data of Japan. So at the time of May 1st, doubling time of Japan is very low. So it means the situation of Japan at that time was not good. Another popular indicator is the basic reproduction number. It is denoted R0 and pronounced R0 or R0. R0 expects the number of cases directly generated by one case in a population, where all individuals are susceptible to infection. The spread of infectious disease can be represented by a mathematical model. If an individual, after getting infected, infects exactly R0 new individuals only after exactly at a time tau has passed, then the number of infectious individuals over time grows according to the following formulas. Here, the time tau is referred to as the serial interval. And this is another mathematical model called SEIR model. So in this model introduces 4 types of populations. One is susceptible. This is an individual who are not immune to an infection. And second type is exposed. Exposed is an individual who is infected but has no symptoms. Third type is infectious. Infectious is an individual who is infected and has no symptoms, but does infect others. And fourth type is recovered. Recovered means recovered people. And in this SEIR model, R0 can be written in this formula. And this is an example of simulation for SEIR model. As you can see, if R0 is less than 1, the number of cases is shrinking like this. And if R0 is greater than 1, the number of cases is growing like this. And especially if R0 is greater than about 1.5, the impact of growth exponentially increases. Therefore, if R0 is greater than 1.5, that means we are in very dangerous situations. And this graph of time series data, this graph shows a time series data of basic reproduction number for 7 countries, Japan, Korea, Indonesia, US, Singapore, Thailand, China. And we can see that during the end of July and the middle of March, some country had a peak and it was a bad situation. Sorry. And for example, this peak is Korea, and this peak is Indonesia, and this peak is United States, and this peak is Thailand, and Japan peak in Japan is here. And as for Singapore, in the end of April, the R0 had a peak in Singapore, and I remember that some news articles mentioned about this situation of Singapore. Singapore is very dangerous because the R0 of Singapore at April is very high. However, until May 1st, R0 looks converged for all countries. And I think this is one of the reasons why government in each country is going to lift the emergency state. And there is another research to study correlation between COVID-19 deaths and BCG vaccine policy. Here, BCG is a vaccine for protecting tuberculosis. And this research is conducted by two researchers from Tokyo Institute of Technology. And in this research, doubling time is used as an indicator. In this study, they classified three groups, each country into three groups. So first one is countries where BCG vaccinate, where not BCG obligated country. Second group is BCG vaccinated countries, and the third group is BCG vaccinated countries using the Tokyo 1721 strain. And they did a Wilcoxon rank sum test, and they found that the doubling time of those two groups were significantly different with p-value 007. Two groups, BCG vaccinated countries and not BCG obligated countries, are quite different with a p-value 0.007. In addition, they also studied about effect of Tokyo 1721 strain. And also found that two groups of BCG vaccinated countries using a Tokyo strain and the other 34 countries are significantly different with p-value 0.026. In addition, I tried additional test, and this is the additional result I got. Please note that I extended the period to April 30. That means the max days are extended from 6 days to 30 days. I tried the same Wilcoxon rank sum test for the extended data. I used MATLAB for the analysis. As a result, I got the same result that two groups of BCG vaccinated countries and not BCG obligated countries are significantly different with p-value 0.0016. I also got the result that BCG vaccinated countries using Tokyo 1721 strain and the other vaccinated countries are significantly different with p-value 0.008146. From these results, when we extended the time series period data to more longer dates, we can find that his research results is true. So that means in my opinion, I want to believe their research result, BCG vaccine is very effective against COVID-19. But this is just my opinion. And as I showed, if you can get the latest data, like me, and mathematical software, you can do the same calculation. You can get the data from web repository, such as provided by Johns Hopkins University, and use the mathematical software, such as MATLAB. Please try it by yourself. If you send me a question, I will answer it to your question anytime. In the beginning of this presentation, I said, by quoting from Bill Gates, it is essentially important to develop vaccine and treatment method. However, it will take much time. Therefore, as what we can do now, it is the best approach to increase testing, such as PCR test, and reduce people contact by shutdown and so on. So in the last part of this presentation, I'd like to introduce promising approaches using information technologies for each problem. First, as for testing, I'd like to introduce COVID-NET. The research title is COVID-NET, a tailored deep convolutional neural network design for detection of COVID-19 cases from chest X-ray images. And this work is led by Linda Wang, Zhong-Qiu Lin, and Alexander Wong, who belongs to University of Waterloo and Darwin AI Corporation. Their motivation is to introduce effective screening of COVID-19. However, the number of PCR test kits is not enough over the world. Therefore, they are proposing a CNN-based screening method to reduce the cost and resources of hospital. And this is an architecture of COVID-NET. The dimension of softmax is 3. And this means this neural network architecture can classify into 3 groups: normal and COVID-19 and pneumonia. And they used source code and dataset they used in the research are publicly available from this website, this GitHub website. And they used 3 resources from 3 different sites and prepared training data set and test data set for neural network like this. All data are images of X-ray images of lungs. X-ray images of lungs. And this slide shows the results from paper. And here, sensitivity means a proportion of actual positives. And the positive predictive value is a proportion of the error. So in their result, both correct rates, sensitivity and PPV, was over almost 90%. Over 90%. So their results show a pretty good result for their proposed neural network to classify into 3 conditions: normal, pneumonia, and COVID-19. This model can classify very well into three conditions: normal, pneumonia, COVID-19. Besides, I also tried dataset available on May 5. Please note that the number of test data increases to 1,510 from 2,231. In the result, although the sensitivity was almost the same result, sensitivity was almost the same result as previous research. However, PBV for COVID-19 was worsened to 0.588 due to the additional test data. However, I think this technology is still interesting and promising for the actual usage in the near future. And finally, I'd like to introduce exposure notification system for reducing people contact by shutdown and so on. So in March or April, Google and Apple are making a joint effort. They are thinking to use Bluetooth technology to help governments and health agencies reduce the spread of virus. And in Japan, from June, Japanese government is recommending to use this application. And this application is called COCOA, COVID-19 Contact Confirming Application. Japanese government currently is recommending Japanese people to use this application. The first, I'd like to explain the scenario using this application before the technical specification. In the scenario, two people, Alice and Bob, was contacting each other. So after a few days, suppose that Bob is infected. After that, this information is sent to the data server using a Bluetooth identifier. When Bob is infected, Bluetooth identifier is sent to a data server, data center. Then Alice continues to download Bluetooth identifier periodically, and she knows she had contacted someone who is infected. At this point, the infected person is anonymous. So this means Alice doesn't know. Alice only knows she contacted with a person who likely infected, but she doesn't know the person is Bob. She does not know Bob might be an infected person. After that, she gets the notification from Health Authority Center and decides to stay at home for social distancing. So based on the notification, she can decide, make a decision to stay at home so that she will not spread her infection state to other people. That is a brief scenario of using this application. And next, I'd like to explain the technical issues. I think there are key technologies in this system. First is a proximity detection without location information, and data exchanges with encryption. And the third one is a value matching for encrypted data from positive user. And the fourth one is a exposure risk level calculation. I'd like to explain each technology from the step by step. As for proximity detection, distance is estimated from signal strength of Bluetooth. We can calculate distance based on the signal strength like this. And this information is broadcasted to other devices. So after broadcasting, each device can scan these Bluetooth information broadcasted. Second, I talked about the data exchange with encryption. Bluetooth device exchange Bluetooth identifier that contains rolling proximity identifier and associated encrypted metadata called AEM. This information is encrypted using a key so that individual privacy is secured. So this is information is encrypted so that information is secured. So after broadcasting these informations, these Bluetooth identifier, each device scan the broadcasted Bluetooth identifier. After that, when the user is positive, diagnosis keys are sent to and stored on the cloud server. Diagnosis keys are sent to a cloud server like this. Thus, Bluetooth identifier can be exchanged between different devices. And after exchanging data, value matching is periodically conducted for detecting contact with infected person. So in the third step, diagnosis keys are periodically downloaded to the devices. Diagnosis keys are periodically downloaded to this device of person A. And here, please note that diagnosis keys are sent from infected people, but who are anonymous. After downloading, the system starts to check there are matching between scanned Bluetooth identifier and downloaded diagnosis kit. So RPI is decoded using the TEK so that we can retrieve ENIN included in RPI. Then matching algorithm try to find there is a matching between both EN and IN data. And if RPI values matches, it means the person A has had, there is a possibility that person A had proximity contact with infected people who are anonymous. Finally, I talk about the last step, exposure risk level calculation. And exposure risk level parameter is like this, contains 4 parameters like this. First one is a transmission risk. This is the level of diagnosis verification. And the second parameter is a duration. This is the cumulative duration of the exposure. And the third one is the days since the exposure incident. And the fourth parameter is attenuation. This is a minimum Bluetooth signal strength attenuation. And using these 4 parameters, this application can calculate exposure risk level. First weighted sum as calculated using calculated by summing these 4 parameters with weight values. Then risk score is calculated by normalizing weighted sum with a summation of each 4 parameters. And this slide shows an example of how to calculate exposure risk level. So in this example, transmission risk parameter is 7, and duration risk is also 7, and days risk is 8, and attenuation risk is 1, just 1. And parameter of each, weighting of each parameter is like this, 75 for transmission risk, and 50 for duration risk, and 50 for days risk, and 25 for attenuation risk. So using these values and weight, we can calculate exposure risk level as 6. And this slide shows a diagram how exposure risk levels can be transferred along with the diagnosis kit. So in this case, infection first, infection risk level, exposure risk level is transferred from Bob to Alice. And Bob's exposure risk is 7. And the next, exposure risk levels for Alice is calculated as 6. After that, if Charles had a contact with Alice, this risk level is transferred from Alice to Charles. In this way, secondary exposure user Charles may be notified by the app for his exposure risk levels. Okay, my presentation is that's all. So in this presentation, I introduced recent works against COVID-19 using information technology. So in the first part, in the first part, I introduced how we can analyze data for time series COVID-19 data. And in the last part, I introduced two technologies. One is COVID-19 to detect COVID-19 cases from chest X-ray images. And the second one is an exposure notification system called COCOA by Apple and Google to detect contact possibility with infected person and infection risk level. And in this presentation, I did not discuss about medical and political issue because I'm a researcher of information technology. But hopefully, we all correctly understand the current situation over COVID-19 and do activities that we can for getting back to our normal life. Okay, so finished. Thank you so much for your attention for my long presentation. And any questions and comments and messages are very welcome. Please send your comments to the following address, takano@ic.kanagawa-it.ac.jp. So thank you so much. Please stay healthy.